Basic calculations. Before a cross-country flight, a pilot should make common calculations for time, speed, and distance, and the amount of fuel required. Converting minutes to equivalent hours. Frequently, it is necessary to convert minutes into equivalent hours when solving speed, time, and distance problems. To convert minutes to hours, divide by 60. Thus, 30 minutes is 30 over 60 equals 0.5 hour. To convert hours to minutes, multiply by 60. Thus, 0.75 hour equals 0.75 times 60 equals 45 minutes. To find the time in flight, divide the distance by the ground speed. The time to fly 210 nautical miles at a ground speed of 140 knots is 210 divided by 140, or 1.5 hours. The 0.5 hour multiplied by 60 minutes equals 30 minutes. Answer: 1 hour 30 minutes. To find the distance flown in a given time, multiply ground speed by time. The distance flown in 1 hour 45 minutes at a ground speed of 120 knots is 120 times 1.75, or 210 nautical miles. To find the ground speed, divide the distance flown by the time required. If an aircraft flies 270 nautical miles in 3 hours, the GS is 270 divided by 3 equals 90 knots. Converting knots to miles per hour. Another conversion is that of changing knots to miles per hour, mph. The aviation industry is using knots more frequently than mph, but it might be well to discuss the conversion for those that use mph when working with speed problems. The NWS reports both surface winds and winds aloft in knots. However, airspeed indicators in some aircraft are calibrated in miles per hour, although many are now calibrated in both miles per hour and knots. Pilots therefore should learn to convert wind speeds that are reported in knots to miles per hour. A knot is 1 nautical mile per hour, nmph. Because there are 6,076.1 feet in 1 nautical mile and 5,280 feet in 1 statute mile, the conversion factor is 1.15. To convert knots to miles per hour, multiply speed in knots by 1.15. For example, a wind speed of 20 knots is equivalent to 23 miles per hour. Most flight computers or electronic calculators have a means of making this conversion. Another quick method of conversion is to use the scales of NM and SM at the bottom of aeronautical charts. Fuel consumption. Aircraft fuel consumption is computed in gallons per hour. Consequently, to determine the fuel required for a given flight, the time required for the flight must be known. Time in flight multiplied by rate of consumption gives the quantity of fuel required. For example, a flight of 400 nautical miles at a GS of 100 knots requires 4 hours. If an aircraft consumes 5 gallons an hour, the total consumption is 4 times 5, or 20 gallons. The rate of fuel consumption depends on many factors: condition of the engine, propeller rotor pitch, propeller rotor revolutions per minute, RPM, richness of the mixture, and particularly the percentage of horsepower used for flight at cruising speed. The pilot should know the approximate consumption rate from cruise performance charts or from experience. In addition to the amount of fuel required for the flight, there should be sufficient fuel for reserve. Another aid in flight planning is a plotter, which is a protractor and ruler. The pilot can use this when determining true course and measuring distance. Most plotters have a ruler which measures in both nautical miles and statute miles, and has a scale for a sectional chart on one side and a world aeronautical chart on the other. Pilotage is navigation by reference to landmarks or checkpoints. It is a method of navigation that can be used on any course that has adequate checkpoints. but it's more commonly used in conjunction with dead reckoning and VFR radio navigation. The checkpoints selected should be prominent features common to the area of flight. Choose checkpoints that can be readily identified by other features, such as roads, rivers, railroad tracks, lakes, and power lines. If possible, select features that make useful boundaries or brackets on each side of the course, such as highways, rivers, railroads, and mountains. A pilot can keep from drifting too far off course by referring to and not crossing the selected brackets. Never place complete reliance on any single checkpoint. Choose ample checkpoints. If one is missed, look for the next one while maintaining the heading. When determining position from checkpoints, remember that the scale of a sectional chart is 1 inch equals 8 statute miles, or 6.86 nautical miles. For example, if a checkpoint selected was approximately 1/2 inch from the course line on the chart, it is 4 statute miles, or 3.43 nautical miles from the course on the ground. In the more congested areas, some of the smaller features are not included on the chart. If confused, hold the heading. If a turn is made away from the heading, it is easy to become lost. Roads shown on the chart are primarily the well-traveled roads, or those most apparent when viewed from the air. New roads and structures are constantly being built and may not be shown on the chart until the next chart is issued. Some structures, such as antennas, may be difficult to see. Sometimes TV antennas are grouped together in an area near a town. They are supported by almost invisible guy wires. Never approach an area of antennas less than 500 feet above the tallest one. Most of the taller structures are marked with strobe lights to make them more visible to a pilot. However, some weather conditions or background lighting may make them difficult to see. Aeronautical charts display the best information available at the time of printing, but a pilot should be cautious for new structures or changes that have occurred since the chart was printed. Dead reckoning is navigation solely by means of computations based on time, airspeed, distance, and direction. The products derived from these variables, when adjusted by wind speed and velocity, are heading and ground speed. The predicted heading takes the aircraft along the intended path, and the GS establishes the time to arrive at each checkpoint and the destination. Except for flights over water, dead reckoning is usually used with pilotage for cross-country flying. The heading and GS as calculated is constantly monitored and corrected by pilotage as observed from checkpoints. Flight planning. Title 14 of the Code of Federal Regulations Part 91 states, in part, that before beginning a flight, the pilot in command of an aircraft shall become familiar with all available information concerning that flight. For flights not in the vicinity of an airport, this must include information on available current weather reports and forecasts, fuel requirements, alternatives available if the planned flight cannot be completed, and any known traffic delays of which the pilot in command has been advised by ATC. Assembling necessary material. The pilot should collect the necessary material well before the flight, an appropriate current sectional chart, and charts for areas adjoining the flight route should be among this material if the route of flight is near the border of a chart. Additional equipment should include a flight computer or electronic calculator, plotter, and any other item appropriate to the particular flight. For example, if a night flight is to be undertaken, carry a flashlight. If a flight is over desert country, carry a supply of water and other necessities. Weather check. It is wise to check the weather before continuing with other aspects of flight planning to see, first of all, if the flight is feasible, and if it is, which route is best. Tutorial 12, Aviation Weather Services, discusses obtaining a weather briefing. Study available information about each airport at which a landing is intended. This should include a study of the notices to airmen, NOTAMs, and the AFD, Figure 15-24. This includes location, elevation, runway and lighting facilities, available services, availability of Aeronautical Advisory Station frequency, UNICOM, types of fuel available, used to decide on refueling stops, AFSS, FSS located on the airport, control tower and ground control frequencies, traffic information, remarks, and other pertinent information. The NOTAMs, issued every 28 days, should be checked for additional information on hazardous conditions or changes that have been made since issuance of the AFD. The sectional chart bulletin subsection should be checked for major changes that have occurred since the last publication date of each sectional chart being used. Remember, the chart may be up to 6 months old. The effective date of the chart appears at the top of the front of the chart. The AFD generally has the latest information pertaining to such matters and should be used in preference to the information on the back of the chart if there are differences. The Aircraft Flight Manual, or Pilot's Operating Handbook, should be checked to determine the proper loading of the aircraft. The weight of the usable fuel and drainable oil aboard must be known. Also, check the weight of the passengers, the weight of all baggage to be carried, and the empty weight of the aircraft to be sure that the total weight does not exceed the maximum allowable. The distribution of the load must be known to tell if the resulting center of gravity is within limits. Be sure to use the latest weight and balance information in the FAA-approved AFM or other permanent aircraft records as appropriate to obtain empty weight and empty weight CG information. Determine the takeoff and landing distances from the appropriate charts, based on the calculated load, elevation of the airport, and temperature. Then compare these distances with the amount of runway available. Remember, the heavier the load and the higher the elevation, temperature, or humidity, the longer the takeoff roll and landing roll, and the lower the rate of climb. Check the fuel consumption charts to determine the rate of fuel consumption at the estimated flight altitude and power settings. Calculate the rate of fuel consumption and then compare it with the estimated time for the flight so that refueling points along the route can be included in the plan. Charting the course. Once the weather has been checked and some preliminary planning done, it is time to chart the course and determine the data needed to accomplish the flight. The following sections provide a logical sequence to follow in charting the course, filling out a flight log, and filing a flight plan. In the following example, a trip is planned based on the following data and the sectional chart excerpt in this figure. Route of flight, Chickasha Airport, direct to Guthrie Airport. True airspeed, TAS, 115 knots. Winds aloft, 360 degrees at 10 knots. Usable fuel, 38 gallons. Fuel rate, 8 gallons per hour. Deviation plus 2 degrees. Steps in charting the course. The following is a suggested sequence for arriving at the pertinent information for the trip. As information is determined, it may be noted as illustrated in the example of a flight log in the figure. Where calculations are required, the pilot may use a mathematical formula or a manual or electronic flight computer. If unfamiliar with the use of a manual or electronic computer, it would be advantageous to read the operation manual and work several practice problems at this point. First, draw a line from Chickasha Airport, point A, directly to Guthrie Airport, point F. The course line should begin at the center of the airport of departure and end at the center of the destination airport. If the route is direct, the course line consists of a straight single line. If the route is not direct, it consists of 2 or more straight-line segments. For example, a VOR station which is off the direct route but which makes navigating easier may be chosen. Radio navigation is discussed later in this chapter. Appropriate checkpoints should be selected along the route and noted in some way. These should be easy to locate points, such as large towns, large lakes and rivers, or combinations of recognizable points, such as towns with an airport, towns with a network of highways, and railroads entering and departing. Normally, choose only towns indicated by splashes of yellow on the chart. Do not choose towns represented by a small circle. These may turn out to be only a half-dozen houses. In isolated areas, however, towns represented by a small circle can be prominent checkpoints. For this trip, 4 checkpoints have been selected. Checkpoint 1 consists of a tower located east of the course and can be further identified by the highway and railroad track, which almost parallels the course at this point. Checkpoint 2 is the obstruction just to the west of the course and can be further identified by Will Rogers World Airport, which is directly to the east. Checkpoint 3 is Wiley Post Airport, which the aircraft should fly directly over. Checkpoint 4 is a private, non-surfaced airport to the west of the course and can be further identified by the railroad track and highway to the east of the course. The course and areas on either side of the planned route should be checked to determine if there's any type of airspace with which the pilot should be concerned or which has special operational requirements. For this trip, it should be noted that the course passes through a segment of the Class C airspace surrounding Will Rogers World Airport, where the floor of the airspace is 2,500 feet mean sea level and the ceiling is 5,300 feet MSL, point B. Also, there is Class D airspace from the surface to 3,800 feet MSL surrounding Wiley Post Airport, point C, during the time the control tower is in operation. Study the terrain and obstacles along the route. This is necessary to determine the highest and lowest elevations as well as the highest obstruction to be encountered, so that an appropriate altitude which conforms to 14 CFR Part 91 regulations can be selected. If the flight is to be flown at an altitude more than 3,000 feet above the terrain, conformance to the cruising altitude appropriate to the direction of flight is required. Check the route for particularly rugged terrain so it can be avoided. Areas where a takeoff or landing is made should be carefully checked for tall obstructions. Television transmitting towers may extend to altitudes over 1,500 feet above the surrounding terrain. It is essential that pilots be aware of their presence and location. For this trip, it should be noted that the tallest obstruction is part of a series of antennas with a height of 2,749 feet MSL, point D. The highest elevation should be located in the northeast quadrant and is 2,900 feet MSL, point E. Since the wind is no factor and it is desirable and within the aircraft's capability to fly above the Class C and D airspace to be encountered, an altitude of 5,500 feet MSL is chosen. This altitude also gives adequate clearance of all obstructions as well as conforms to the 14 CFR Part 91 requirements to fly at an altitude of odd 1,000 plus 500 feet when on a magnetic course between 0 and 179 degrees. Next, the pilot should measure the total distance of the course as well as the distance between checkpoints. The total distance is 53 nautical miles, and the distance between checkpoints is as noted on the flight log in this figure. After determining the distance, the true course should be measured. If using a plotter, follow the directions on the plotter. The true course is 031 degrees. Once the true heading is established, the pilot can determine the compass heading. This is done by following the formula given earlier in this chapter. The WCA can be determined by using a manual or electronic flight computer. Using a wind of 360 degrees at 10 knots, it is determined the WCA, wind correction angle, is 3 degrees left. This is subtracted from the true course, making the true heading, TH, 28 degrees. Next, the pilot should locate the isogonic line closest to the route of flight to determine variation. The sectional chart shows the variation to be 6.30 degrees east, rounded to 7 degrees east, which means it should be subtracted from the TH, giving an MH of 21 degrees. Next, add 2 degrees to the MH for the deviation correction. This gives the pilot the compass heading, which is 23 degrees. Now, the ground speed, GS, can be determined. This is done using a manual or electronic calculator. The GS is determined to be 106 knots. Based on this information, the total trip time, as well as time between checkpoints, and the fuel burned can be determined. These calculations can be done mathematically or by using a manual or electronic calculator. For this trip, the GS is 106 knots and the total time is 35 minutes. 30 minutes plus 5 minutes for climb, with a fuel burn of 4.7 gallons. Refer to the flight log for the time between checkpoints. As the trip progresses, the pilot can note headings and time and make adjustments in heading, GS, and time. Filing a VFR flight plan. Filing a flight plan is not required by regulations. However, it is a good operating practice, since the information contained in the flight plan can be used in search and rescue in the event of an emergency. Flight plans can be filed in the air by radio, but it is best to file a flight plan by phone just before departing. After takeoff, contact the AFSS by radio and give them the takeoff time so the flight plan can be activated. When a VFR flight plan is filed, it is held by the AFSS until 1 hour after the proposed departure time and then canceled unless the actual departure time is received, a revised proposed departure time is received, or at the time of filing, the AFSS is informed that the proposed departure time is met, but actual time cannot be given because of inadequate communication. The FSS specialist who accepts the flight plan does not inform the pilot of this procedure, however. This figure shows the flight plan form a pilot files with the AFSS. When filing a flight plan by telephone or radio, give the information in the order of the numbered spaces. This enables the AFSS specialist to copy the information more efficiently. Most of the fields are either self-explanatory or non-applicable to the VFR flight plan, such as item 13. However, some fields may need explanation. Item 3 is the aircraft type and special equipment. An example would be C-150/X, which means the aircraft has no transponder. A listing of special equipment codes is found in the Aeronautical Information Manual, AIM. Item 6 is the proposed departure time in UTC, indicated by the Z. Item 7 is the cruising altitude. Normally, VFR can be entered in this block, since the pilot chooses a cruising altitude to conform to FAA regulations. Item 8 is the route of flight. If the flight is to be direct, enter the word direct. If not, enter the actual route to be followed, such as via certain towns or navigation aids. Item 10 is the estimated time en route. In the sample flight plan, 5 minutes was added to the total time to allow for the climb. Item 12 is the fuel on board in hours and minutes. This is determined by dividing the total usable fuel aboard in gallons by the estimated rate of fuel consumption in gallons. Remember, there is every advantage in filing a flight plan, but do not forget to close the flight plan on arrival. Do this by telephone to avoid radio congestion. We hope you learned a lot. Please help us spread the word about Pilot Training System, and we look forward to further servicing your flight training needs.